Okay, so we will continue with our discussion on motion in 2 and 3 dimensions. Now, oftentimes the best way to solve a two-dimensional problem is by treating it as two separate one-dimensional problems. That's usually the strategy. Okay, we look at it as an x-axis or a horizontal problem and a y-axis or vertical problem, and they're kind of connected together, uh, in the two-dimensional problem, but we solve each dimension individually. Okay, so if an object moves with some velocity v at an angle theta, then what we want to do is break that velocity into vector component form. That's another reason breaking vectors into components is so important, because what we'll use then is the x velocity to solve the x part of the problem and the y velocity to solve the y part of the problem. So as we look at this page right here, and we see our diagram, showing our vector, let's say v0, our original velocity of some object, whatever that object may be. If it's launched at some angle theta here with respect to the x-axis, then we know that we can get the size of the components of the velocity by taking the size of the original velocity, that would be its speed at the beginning of the problem, right? That's the size of the velocity vector is the speed. So basically how fast it's going times the cosine of the working angle to get the size of the x component. We take the size of the vector, which is its length, times the sine of the angle, right, the working angle, to get the y component size of the velocity. Now here both velocity components would be positive because the velocity vector points over in the positive x direction and positive y direction. It's a combination of to the right and up. And so those both would be positive components. Obviously, if the vector was pointing over here like this, that would be a negative. We'd put a minus sign in front of our v0 cosine theta there, and we'd have a positive v0 sine theta. So the signs, remember, we get our signs of our components by looking at the diagram. So these diagrams that we draw are very, very important always, and they continue to be important even in the two-dimensional problems. So the good news here is if you have gotten comfortable solving one-dimensional problems, then two-dimensional problems aren't going to be a whole lot harder. The bad news is if you're still struggling with one-dimensional problems, then going into two-dimensional motion almost doubles your trouble. Okay, so you definitely want to keep pounding away and working on those one-dimensional kinematics problems and getting that ironed out, getting your signs and your understanding of different directions and what how the equations work. Get that all ironed out, and then two-dimensional problems will not be that much harder. And of course, solving problems in 3 dimensions or 3D is similar. You just deal with one dimension at a time. So, we start in 1 dimension. Now we work on understanding it in 2 dimensions. And then you can always extend this to 3 dimensions, which just is a little bit more complicated. Okay, so there's a particular type of two-dimensional motion here that we want to narrow in on and look at in detail, and that's called projectile motion. When an object's tossed across the room, it takes a free flight path through the air. In other words, we're talking about small, dense objects right now because we want to ignore air resistance, all right? We know that when we throw something across the room or across the yard, there's going to be some air molecules hitting against it, affecting its motion some. But right now we're dealing with something like, maybe imagine a golf ball that's very dense and heavy, and we toss it across the room. It's small enough and it's dense enough that the air resistance is not going to make much of a difference in its path. As a matter of fact, so little difference in its path that we might as well ignore it and say it's having no effect on it. And that's kind of what we're doing right now. It's kind of like that idea of free fall, except we're tossing the object through the air now, with some sideways motion, but we're still looking at it as free fall. The only force acting on the object after we toss it is going to be gravity. Okay, and in this particular case, if that's the case, then the acceleration in the x direction would be 0, right? Because there's going to be nothing pushing or pulling on the object in the left or right direction after we throw it, right? So there's no acceleration in the x direction, which means the velocity in the x direction doesn't change. The final x velocity at the end of the problem will be the same as the object's x velocity at the beginning of the problem, or its original x velocity, right? In the y direction, the object is under the influence of gravity only, because this is, we're ignoring air resistance, and so the acceleration in the y direction is, of course, minus g. So some examples of some sports where projectile motion is important. is some sports like tennis, baseball, football, lacrosse, racquetball, soccer. Again, some of these at professional levels, the air resistance does become a factor that can cause interesting things like, in baseball and tennis, you can get curve on the ball because of its spin and so forth. Some of these sports, to really accurately model them with the physics, we'd have to consider air resistance. But we can get really close. We can get pretty, really good approximations in these with these sports by using this idea of just projectile motion. So how do we do this? Well, with projectile motion, when we look in the x direction, again, there's no acceleration. And so interestingly enough, if I write down our equations, our kinematic equations, assuming the x direction here, these are the equations we had back in chapter 2. These were our main equations, right? V final x equals V original x plus acceleration times time. And then our last one here, V final x squared equals V original x squared plus 2 times acceleration times x final minus x original. So what we had was, those are our 3 big equations that we set in kinematics that we could use to solve problems. In this particular case, with projectile motion, we just talked about the fact that there is no acceleration in the x direction. So that means this term, and this term are all going to go to 0. And what's that going to leave us with? Well, what that's going to leave us with is, look at the bottom equation. V final x squared equals V original x squared. Or if you take the square root of both sides, it says the same thing as the second equation there, which is V final x equals V original x. So in other words, with no acceleration, the velocity along the x direction stays the same. No surprise. And that leaves us pretty much with one fairly simple equation here, that x final equals x original plus v0x times t. So when we do projectile motion, the equations for the x direction are pretty simple because it's just this one. So you really can't go wrong picking the equation for the x direction. That's what it's going to be. So it's kind of like a no-brainer in the x direction, right? Now in the y direction, as we consider the motion in the y direction, it's just gravity pulling the object downward as the projectile flies across the room. And so what we end up with over on this right yellow box here is we end up with, of course, our free fall equations, right? So if we talked about something being tossed up into the air or dropped and it was under the influence of only gravity, we had these equations. And of those equations, once again, we basically said the first 3 are the most important, right? These have to do, these are can be used, but they're not, what I have found is that these 3 are really powerful, and you can solve just about any problem just using those 3 equations right there. Okay, and so if you focus in on those, you've got 3 equations for the y direction, you've got 1 for the x direction, and boom, you're ready to solve problems. And so that's what we want to take a look at here next. How do we go about solving problems with these? Well, again, we typically will start with the simplest type of problem when we're learning something for the first time. And so the simplest projectile motion we can get is really where the object is fired or released horizontally. So if we talk about launching something horizontally, throwing a ball out level with respect to the ground, initially level, or an airplane flying along level that drops something, right? And as it drops, it falls to the ground, okay? These are examples of simple projectile motion where the angle of launch is 0 degrees. That is, all the motion is initially in the x direction. So in this particular case, our original x velocity is just going to be equal to whatever the launch speed was, and our original y velocity would be 0 because the object's not being launched upward or downward at any angle, right? Theta here, no theta here, no theta here. It's being launched perfectly horizontal, which means if we look at that vector, it has no component in the y direction. It's all v0. So in other words, v0x is v0, and we have nothing in the up and down direction, right? No motion in the up and down direction, so the original velocity in the y direction is 0. So that's a simplification, and that's a good problem to start. Okay, so let's take a look at this, an example that's something like that. So suppose you shoot an arrow horizontally at 20 meters per second. So presumably we're talking about an archer with a bow and arrow shooting an arrow horizontally. at 20 meters per second. It says if your target is on a tree 5 meters away and you aim perfectly at the center of the target, then how far below the target will your arrow hit the tree? Okay, so when we get a question like this, after maybe rereading it again, we want to draw a sketch and make sure we get an accurate depiction of what's happening. Now, I set up my picture with clip art. Your diagram and your sketch, of course, don't have to be nearly this neat and colorful looking. But when you do this, sometimes when you use clip art, you may find, for example, this guy, he looks like he's maybe shooting the arrow upward a little bit. So sometimes it doesn't even help to use a clip art. But anyway, so the arrow here is really being shot perfectly horizontally. So I'm going to go ahead and kind of sketch in an arrow like this to help us remember that archer is shooting the arrow perfectly horizontally, and presumably they're eyeing it up so that it goes right to, well, let me see if I can draw that a little better. It's hard to draw here nice and straight, but that's going to go right, they're aiming right to the center of that target there. Okay, and after they launch it, we know obviously in reality, gravity is going to pull the arrow down a little bit. And so the arrow is actually going to land somewhere down here while we were aiming at it here, and that's because of gravity. Okay, so I've got my picture set up, and if you had set it up differently than I am, let's suppose you had set it up with the archer shooting the arrow to the left and having the tree over to the left, have the tree over here or something. That's fine. You just have to be consistent with setting up your coordinate system and be consistent with your signs and so forth. Okay, I think most of us typically set things up moving left to right because that's kind of the positive direction, and it's also the direction we read, from left to right across a line. And so my guess is most of us would probably set it up going left to right, even though they didn't say anything up here about that, right? I mean, they didn't really tell us which direction. That's part of what we get to choose. The other thing we get to choose is our coordinate system. And again, I don't have to start the arrow at position 0, but why not? I mean, I could, if I wanted, I could say, well, x0, let's just call x0 10, and then x final over here where it hits the tree, x final in that particular case would be 5 meters more positive, or 15. That would be okay. I could do that. There's nothing wrong with that. But more often than not, if we don't have another good reason to select something other than 0 for the original position, we select 0 for x0, and that means my x final over here where the arrow hits the tree is 5 meters away in the x direction, right? They told me that. They told me the tree is 5 meters away. And so x final is 5, x original 0. I jot that information down. Now, that's my 0 and my x axis. I can't change that now that I've selected it. In the y direction, I get to choose where the y equals 0 level is as well. Now, a lot of times I'll think of the ground as being y equals 0, right? And if they'd have told me what height that this arrow was leaving from, I could make my y original equal to whatever that height was. Maybe it's 1 meter off the ground. But they didn't really tell me that here. So even though I could guess at it and it would be okay, I'm just going to go ahead and I'm going to say, well, let me just choose the original height that the arrow launches from as my 0 height. Okay, and that means it's going to end up over here. This would be where y equals 0 is, right? If I come across the page parallel to the ground. But my y final is down here somewhere. My y final, because gravity pulls the arrow down, y final, where the arrow lands over here and hits the tree at, okay, is going to be my y final coordinate height. And I expect that to be below y equals 0. So I'm expecting y final here to be a negative number at the end. Right? So once I've chosen my y equals 0 as being the height the arrow is launched from, then I expect y final to be a negative number. Now, what else do I know? Well, what I know is that they launch it here at an original velocity in the x direction of 20 meters per second because they're launching it horizontally. So all that initial speed is in the horizontal direction, and none of it's in the y direction. So v original y would be 0. Right? So I get all this set up, got all my original variables listed. I've got my coordinate system all set up. I've got the thing all set up, ready to go. And now what do I do? Now it's time to select an equation. At this point, since I'm looking for y final, I might be tempted to go and look in the y direction first, and that would be okay. And I'd have several equations to choose from. I'd want to find an equation that had y final in it, and then I'd want to try to see if I had an equation that had all the other variables in it. In this particular case, if we do that, there's nothing wrong with doing that, but what we're going to find is we're not going to find an equation for solving for y final right out of the gate. Okay? and that's because we don't have quite enough information to solve those equations in the y direction completely yet. We could solve for other things, but not y final. Now, in the x direction, there's only one equation to choose from. So sometimes when you're doing this, you might just want to start in the x direction because you know that's a no-brainer on the equation. There's only one equation to choose from, and that's x final equals x original plus v0 xt. Now, we know x final is 5. We know x original. We selected the arrow starting at position 0. We know 20 meters per second, standard units, for our original x velocity, right? And so we can do that. We can write, substitute in for each of these variables that we know. That leaves us with one unknown, t. And if we solve that out, we're going to get the time that it takes for the arrow to reach the tree. Notice that this equation has no y's in it. In other words, this time here that it's going to take for the arrow to get to the tree is going to be independent of what happens in the vertical direction. So there I have my equation, 5 equals 0 plus 20 meters per second t. We solve it out, and we find out, look, t is a quarter of a second. In 1/4 of a second, the arrow is going to get from here to the tree. Okay, it's going to leave from here and get to the tree. That's what's happening in the horizontal direction, right? In the vertical direction, it's falling a little bit during that time. And now that we know how much time it's falling, we can go to the y direction and finish solving this problem. Okay, so now we go to the y direction equations and we try to find an equation that has a y final in it, but one that we know everything else in, right? Because we want to solve for y final. That's what we're trying to figure out is, what is y final? What's this y final height where the arrow hits the tree, right? We know it's going to be negative because of the way we set this up. But what values are going to be? So we have an equation here of the y final. Do we know y original? Yeah, we selected y0 as 0. We decided to set the original height of the arrow when it left the archer's bow as 0, at a height of 0. Do we know v original y? Yeah, that's actually 0. Since it was launched horizontally, v original y, the original velocity in the y direction, is 0. So we know that. Do we know t? We do now. We do know t now. And do we know g? Of course we know g. G is just, if we're in standard units, if we are using things in standard units, which we are here, g is equal to, see, I almost did what I'm always telling you not to do. G is equal to 9.8 meters per second squared, all right? Remember, our minus sign in the equation has already been taken care of here. Everywhere you see a g, it's just the magnitude of the acceleration of gravity. That's what g stands for, not negative 9.8. G is equal to positive 9.8. And so that goes in for g. We know t is quarter of a second. We know v original y is 0, and we know y original is 0. So this term and this term are zeros, and we end up with just y final equals negative 1/2 times 9.8 times 0.25 squared. Now here I've demonstrated for you this process of saying, well, let's simplify our math by just making g equal to 10. G is approximately 10 meters per second squared. And you can do that and get roughly correct answers by doing that. Okay, so sometimes if you're trying to very quickly on a test question determine which multiple choice answer is correct, sometimes using g as 10 speeds up the mathematics and helps you get to the answer a little bit quicker. You don't have to do that with today's calculators, being so available, and usually you have the calculator during the test and so forth. There's really hardly any reason not to use g equal to 9.8 meters per second squared. But if you didn't want to, if you wanted to, if you were doing this on a piece of paper and wanted to speed up the math perhaps a little, you could use g as 10. And when we do that here, if we use g as 10 and we solve this out, we get y final is equal to minus 0.3125 meters, which is not quite a foot maybe, but about a foot. So in other words, the arrow comes in. If there were no gravity, it would have hit right at the center of the target, right? But with gravity, it deflects, and it's going to hit down here, and we're going to miss the target by maybe putting it into English units of by about a foot. Okay, that's a pretty big difference. And so in that 1/4 of a second, that arrow falls almost a whole foot, and we miss the target pretty dramatically. So in order to hit the target in this case, we would have to aim our arrow, a little above the horizontal. So as gravity pulls it down, it ends up back at the same height as our target, right? We'd have to give a little bit of upward y velocity to compensate for the amount of time that it's going to be falling due to gravity. And so that's what makes being a good target shooter, whether it's archery or rifles or whatever. If you're a good sharpshooter, you learn how to account for that. You learn how to understand the amount of time involved based on the range of your target. Even when you bring in air resistance, then it gets even more complicated because you might have wind deflecting it a little bit as well. But you can see that the basics of this is described with the equations of physics. We can model this simple harmonic, or this, projectile motion, and we can solve for the final position of the arrow. So there's an example of a projectile motion problem. So we solved that two-dimensional problem by breaking it into two one-dimensional problems. We broke it into components, x and y. We looked at its position in the x direction. We looked at its position in the y direction. We looked at its velocity in the x direction, its velocity in the y direction. And then we knew there was no acceleration in the x direction, and the acceleration in the y direction was minus g. So our equations were all set up for that. Okay, so we broke it into two one-dimensional problems, and we basically solved those one-dimensional problems on their own. The key here is that those equations are linked in time. They are linked in time. The t in the x equations was the same as the t in the y equations, right? So both t's in the x and y part of the problem are the same t. That's the amount of time from the beginning of the problem to the end of the problem. So, both problems had the same original t original and the same t final. So whether we're talking about the x direction or the y direction, right, the times were the same. And so we have one variable t that's in both our x and y equations, and that's the same t. So that's the key thing, and it kind of ties those two problems together. Okay, and so as mentioned previously, this type of motion is a special type of motion that we're looking at here is called projectile motion. And in each of these cases, objects are basically being projected or launched or thrown into the air, and they're moving freely through the air. That's what we mean by projectile motion. So one key thing that you hopefully maybe started to pick up on in this projectile motion is that what's happening in the horizontal direction, this way, has no effect from what's happening this way. So that means that if we dropped a ball and we launched another ball horizontally at the same time, right, the motion, the ball that's dropped, of course, will fall faster and faster and faster as it falls, but the one that's launched horizontal will go the same distance sideways, but it will, with each moment of time, but it will also fall the same distance as the one that was dropped per unit time. So in other words, the horizontal and vertical motions are kind of decoupled. They're linked in time, but the motions are not affecting each other. And so here we see in a photograph, this is a photograph made with an old-fashioned camera that the shutter was locked open, and then there was a strobe light flashing. And we see a red ball and I guess a yellow-green ball here. Both of them were dropped released at the same time. The yellow-green ball was launched horizontally. The red ball was simply dropped. And what do you notice? What you see in this is that the height of the red ball and the height of the yellow ball as they fall are pretty much staying the same, right? In other words, the motion sideways for the yellow ball, it's chugging along at a certain sideways motion, and so the gap between its x positions is nice and steady. I can't draw this as well as I'd like to, but this distance here is staying steady horizontally, but vertically it's falling the same way as the red ball did. So the motion sideways of the yellow-green ball did not affect how gravity acted on it. Okay, sometimes students think that if something's launched horizontally very quickly that it doesn't fall as fast, but that's a misconception. As soon as you launch a bullet from a gun horizontally, right, that bullet, as soon as it comes out the end of the gun barrel, is starting to fall, right? It's just that the bullet's moving so quickly that it usually gets to the target so quickly that our brain kind of makes up this rule that, oh, things that are going fast sideways don't fall very quickly. But that's not true. If I were to launch a gun, if I had a rifle here, and I took the gun and I shot a bullet out of the end and shot the bullet horizontally, perfectly level, and at the same time somebody else took a bullet and dropped it, those bullets are going to hit the ground at the same time. The amount of time it takes for that bullet, bang, gun's shot, boom, it falls to the ground. That blink of an eye or short period of time from dropping, that takes for a bullet to go from the height of the gun barrel to the ground, if it were dropped, that's the amount of time it takes for the bullet to land. The bullet would end up on the ground in the same amount of time. It's just that it's moving so fast sideways that usually it's hitting the target before it's fallen very far, because guns shoot bullets very quickly. And so again, we kind of falsely think that things that move sideways, that it affects how fast they fall, but it doesn't. Everything falls and accelerates towards the earth at about 9.8 meters per second per second. In other words, for each second it's been falling, it's going to be falling at a rate of 9.8 meters per second faster than it was the second before. And if you remember, there's a simple way to keep our, if you're thinking, well, 9.8 meters per second, is that fast? Again, as American students, it sometimes is difficult to remember whether that seems fast or not. Remember, 25 meters per second is about what? It's about 56 miles per hour. So highway speed is about 25 meters per second. So if I drop something, after 1 second, it's moving downward at 9.8 meters per second. That's how fast it's moving. After another second of falling, it's now moving at twice that, or about 19.6 meters per second, right? So between seconds 2 and 3, if I drop something, after 1 second, it's moving that fast. After 2 seconds, it's moving that fast. Before it even gets to 3 seconds, it does not have to fall for even 3 seconds to get up to highway speed. Okay? So that kind of helps put some of that into perspective as well. See an animation that hopefully help put some of this into perspective. Notice down here at the bottom right, I have controls for gravity and horizontal velocity. So what I'm going to do first is I'm going to turn off gravity. That would be something that would be kind of interesting if we could do on planet Earth, wouldn't it? In a physics classroom. Well, at least with the computer we can do that. So if I turn off the gravity and I press play and I have horizontal velocity on, what I find is that the ball is, shoots out horizontally, and it goes the same distance per unit time. So it's kind of like a strobe light flashing here again, where every time, it's just flashing at a steady rate. And so every time the strobe light flashes, we mark where the ball is, okay? And so what we see is that the ball is moving steadily in a horizontal direction. Now, if I turn off the horizontal velocity, but I turn on gravity, and I release the ball again from right up here, what we find, of course, with no horizontal motion and gravity on is that the ball falls. And of course, because gravity is continuously pulling down on the ball, it falls faster and faster and faster as gravity pulls on it. Okay, and so the distance that it falls initially is not very far, right? As early on in its motion, it's not falling very far between the flashes of light. But later on in the problem, after it's had a chance to get really moving much quicker, the distance that it's traveling between flashes of light has increased. And so the graph over here that's straight up and down shows the motion of the ball, true motion of the ball if it were dropped on a planet with gravity, Earth gravity, but had no horizontal motion. It was just simply dropped from rest. Up here is the motion that would happen if there were no gravity and the ball was just moving horizontally. What if we turn both on? Well, if we turn both of these on and we launch the ball, we kind of roll it off the end of that little table there, what we get is that the path of the ball does something like that. And you'll notice that what's happening is each time the strobe light flashes, look where the ball is. When we turn on both the horizontal velocity and gravity, it goes the same distance per unit time in the x direction as it would have if there were no gravity. And in the y direction, it falls below the height of the table there by the same amount in the same amount of time as if it were simply dropped. So the true path of the ball shown here, right? Hopefully you see my arrow moving along here in this animation or this video of this that I'm showing you here. That path is the true path of the ball. And notice that it's simply a combination between free fall, right, along the left side, and steady, constant speed motion, constant velocity motion along the top. It's a combination of that. It's where those times where the strobe light flash, where those would intersect, is where the true position of the ball is. And so again, we see that what happens horizontally and what happens vertically here can be decoupled or thought of as two separate problems, but they're linked, of course, in time. In other words, the amount of time it took to fall here would be the same amount as of the time it took to get here horizontally. And so the true position of the ball, when we combine them, is there, and we see this path of the ball. Hopefully that helps this make more sense to you. So let's try another simple horizontal trajectory type question. It says, suppose a boy throws a baseball horizontally from a height of 44.1 meters. If the ball hits the level ground 90 meters from the base of the throwing tower, then how far did the boy throw the ball? Again, step number one, we want to get a sketch of what's going on. And so here's a kind of a crude little sketch. Again, I used the drawing program, but still did it myself, made it a little more crude looking. And so here we see the tower that's being thrown, the boy's up on top of, that's kind of the height he's throwing it from. We'll say that the height from where he launches the ball to the ground is 44.1 meters. We see that listed along the left side of the diagram. And then when the ball leaves the boy's hand at the edge of the base of the tower, we're told that the ball lands on the ground 90 meters from the base of the tower. So along the horizontal direction, the ball lands over at the end of that 90-meter stretch. So once we've got our little sketch made, then we have to choose our coordinate system. I chose x original as 0, which means x final here is going to be 90. The ball is going to land over at position 90, right? If we look in the y direction, y original, I decided to call 44.1. I can do that. Remember, I have the choice. I have the freedom over defining my coordinate system. So I called the position where it starts there x0 equals 0, and this is x final equals 90. But I decided to call the height at which it starts here. So y original, I decided to call 44.1, which means when it lands, y final, when it lands over here on the ground, y final is going to be 0. Okay? You can do that. Once again, as long as the original launch height is 44.1 meters higher than the final height, we're good. So if you had called this 0 up here, let's suppose you had called it 0 up here, you stuck with the convention of the book and many others by saying, well, just choose the original position of the object when it's launched as being at 0, 0. So if you choose the center of your coordinate system right up here where the ball is launched, right up here is your 0 of your coordinate system, the origin, then y final down here would have to be what? It would have to go into your equations as minus 44.1. Right? Polarities matter. Whether they're, the positions above or below makes a difference. So if this is y original equals 0, then y final would have to be 44.1 meters less than y original. So again, I just did it the other way around, right? I said, well, let's call y original 44.1, and then y final is 0. And so I've got these initial coordinates set up for the beginning point and the end point in the problem. Remember, every physics problem has a well-defined beginning and end. Right? Now, v original x and v original y, they didn't tell me v original x in this case. So this one's a little different. They didn't tell me how fast I threw the ball. That's actually what we want to figure out. They want us to figure out how fast did the boy throw the ball. But what we do know is if it was thrown horizontally, right? If it was thrown horizontally, level with the ground, then y original, or v original y, the original y velocity would be 0. It wasn't thrown with any kind of an upward or downward velocity. It was thrown perfectly horizontally. Okay? And so there's our setup. So turning to the x direction, why not? Because there's only one equation in the x direction, right? So x final equals x original plus v0 xt. So we go ahead and plug in what we know. Do we know x original? Yep. Do we know x or x final? Yep. Do we know x original? Yep. Do we know v0x? No. Do we know t? No. So when I plug these things in, I end up with an equation here that just says 90 equals v0x times t. So I cannot, even though there's only one equation here, I can't solve the x direction equation, at least not initially. So since I want to get this, then how am I going to figure that out? If this equation is true, then if I could figure out t, if I could get my t value, then I would be able to solve for v0x. And so what do I do now? I turn to the vertical motion or the y direction equations to see if I can get the time that it takes for the ball to go from here to here from the y direction equations. If I can, then I can come back to this and finish solving the question. So continuing on, again, in the y direction, we had the ball starting from a height of 44.1. It ends up at a height of 0, and the original y velocity was 0. So we know all that, and we're looking for something that would have t in it. So I pick through my equations and I say, well, this equation right here, I know everything in that equation except t. I know y final was 0. I know y original was 44.1. I know v original y is 0. And I know g is 9.8. So I know everything in that equation except t, right? One variable that I don't know. So I should be able to solve that. And so I go ahead and I start plugging in the values that I know for these things, right? And I end up with, since this cancels out, I end up with an equation that says 4.9 t squared equals 44.1. I divide both sides by 4.9. So I end up with t squared equals 44.1 divided by 4.9. Then I take the square root of both sides, and of course I get an answer here really of plus or minus 3 seconds. Obviously, time only goes forward. I can't have an answer of minus 3 seconds for the ball to go from here to here. And so the positive root in this case, 3, is the right answer. And we get 3 seconds for the amount of time it takes the ball to go from here to here. And you're going to say, well, wait a minute, doesn't it depend on how fast he throws it? No, it doesn't. If he throws it horizontally, if he threw it faster, it would still take 3 seconds to land. It would just go further horizontally. If he threw it slower, it would still take 3 seconds to land. It would just go for less distance horizontally. So interestingly enough, when it's launched horizontally, it's going to be on the ground in 3 seconds from that height, no matter how fast he throws it. And that's kind of interesting, and that's important. And now, of course, since we know the ball was in the air for 3 seconds, we can go back to the x direction problem and really easily finish this off. If 90 is equal to v0x times the time, then we plug in for t 3 seconds, right? Because that t in the x direction equations is the same as the t in the y direction equations. And now we solve it out and we get v0x, the original x velocity, was 30 meters per second. Okay, 30 meters per second. Now the question is that fast, right? Should this boy go try to, go try out for the New York Yankees or something, or the Los Angeles Dodgers or whoever you like? Okay, is that a good pitching speed, in other words? Well, keep in mind 25 meters per second is about 56 miles per hour. Okay, and so when you think about that, if you know anything about professional baseball, 30 meters per second, oh, I don't know, what's that getting up into? Maybe the 60s, maybe close to 70, something like that. But unless he's throwing a knuckleball or has some really good movement on the ball, that is not going to be fast enough, because most Major League baseball pitchers pitch 90 miles per hour plus, at least their fastballs. And so again, if he has, throwing it at this speed, if he has a good knuckleball or something, he might be successful. But at the Major League level, he does not have a Major League fastball if that's his fastball. And he shouldn't feel bad, because he's still got a better arm than I do. Anyway, all right. Okay, now here's an animation. We're going to launch this ball here. It's kind of a very small little particle ball in this coordinate system. We see our y-axis along the vertical and our x-axis along the horizontal. And we're going to launch this ball. And what we see here is 3 different arrows. The main arrow in the middle there, that's at the 45-degree angle, that's the velocity vector for the ball that we're launching. And so you'll see as the ball goes, the length of that vector will change some, and its angle will change as the ball goes through the air. The other 2 arrows, this one here is the vertical velocity of the ball, and the one here in the horizontal direction is a horizontal velocity, or the x velocity of the ball. So we got v sub y and v sub x basically showing. And as the ball moves through the air, I want you to watch these vectors. The horizontal vector, of course, will stay the same size. This vector down here will stay the same size the entire time the ball's in motion, whereas this vertical vector here, this vertical velocity, horizontal or y velocity vector component, will shrink in length until it gets to 0 at the top of the trajectory, and then it will start to grow towards the negative direction. So this y velocity here, okay, arrow, is going to shrink and then grow in the negative direction at a rate of 9.8 meters per second, whereas the x velocity maintains. And so this actually, when you think about the vector summation, right, this vector, this true velocity vector of the projectile, the true velocity of the ball as it moves, is along the direction of the path, but it's defined by the, combining, it's a vector sum of the x velocity and the y velocity. So it kind of explains, as this y vector shrinks and then grows to the negative direction, and the fact that this one stays the same length, that helps you understand why this angle of this velocity for the ball changes as it goes across the screen. So let's take a look and watch this happen. Again, notice the horizontal vector stays the same length. The y velocity, the y component velocity goes from positive to 0 up at the very top, and then to negative. But notice at the angle, one more time, let's play it again. Notice at the angle that this velocity vector here points at is kind of the vector sum. You think of the parallelogram method there of adding the vectors. That angle and that length there is defined by the components. And so we can still continue to look at this motion as being two separate things combined into one motion that we call two-dimensional motion. Okay, now to wrap things up today, let's have you try one of these problems on your own and see how you're doing. Suppose an airplane flying horizontally at 80 meters per second drops a package from a height of 500 meters. How far away will the package land from the point that was directly below the plane at the time of release? So again, sometimes you have to reread questions a couple times to make sure you understand what they're describing. It's really important to get an accurate setup. So I'm going to show you a little animation here that will hopefully help you better visualize what this problem is asking. Okay, so here we'll see an animation of this airplane or this bomber here flying along horizontally, and it's going to release the package at this point, and the package is going to follow this parabolic trajectory that the projectiles follow. It's going to follow the parabolic trajectory and land over here in the target area. This question is asking about the distance from the point that's directly below the airplane at the time the package is released to where it lands on the ground over here. So again, hopefully if I run this and you can visualize this, the package is being dropped, it's falling because it's moving at the same speed as the airplane, all right? It's always going to be directly below the airplane, interestingly enough, if we ignore air resistance, all right? And so the package is being dropped at this point, it's landing here, and we want to know this horizontal distance. Now this package, of course, in this case looks like a bomb, and of course in World War II and wars of that era, the bombing was done, it's basically with projectile equations and projectile calculations like we're learning in this course. But of course, if it makes you feel better, you could change this problem to a humanitarian package. You know, maybe that package is dropping down there, has food and supplies for some people that have undergone experienced a natural disaster or something like that. So it doesn't have to be a bomb if you don't want it to be, but that's the kind of at least this helps you visualize what the question's asking about. Okay, so here we are back at the problem. Again, I'm going to help you out just a little bit further by kind of showing you that diagram there. So here we have the airplane flying along horizontally at 80 meters per second, nice and level with the ground horizontally. It's 500 meters off the ground, and it's going to drop this package, humanitarian supplies, for example, and it's going to land over here. We want to know what distance, where the question mark is there, we want to know that distance sideways that the package goes. Okay, so you've got to set this up with a coordinate system. I went and set it up this way. All right, so I'm going to get you off to a good start by, you don't have to set it up this way, but again, notice again, x0 is 0, x final is what we're looking for. How far down range does this package land? I chose y original as 500. That makes y final, where the package lands, 0. If you'd have chosen y0 as 0, then what would y final be? It would be negative 500, right? So in other words, y original has to be 500 units positive more than y final in this case. Y original is above by 500 meters, y final. Original x velocity for the package, it would be the same as the airplane, 80 meters per second. And because it's launched horizontally, v original y is 0. So go ahead now, pause the video, and see if you can work out and determine how far that distance is that's indicated with the question mark. That is, what is x final in this particular problem? So go ahead and pause the video at this time, and then you can restart it to see how you did. So we have to figure out the time before we can get x final. Hopefully you realize that. If you go to x final or the x equations to solve for x final, you realize that you have to get time because you have, again, an unknown here. You don't know x final and you don't know t. So we've got to go to the y direction equations to get t. Okay? And so when we look in the y direction equations, hopefully you picked one that you could solve. Sometimes you don't have, sometimes you can take a couple of steps. You can maybe solve two different problems in the y direction to get the time. There's nothing wrong with that, but you shouldn't be afraid to get quadratic equations either. In other words, don't be afraid to use the equation here, y final equals y original plus v0 yt minus 1/2 gt squared. In this particular case, since v0y was 0, we didn't end up with a complicated quadratic anyway. Okay, again, I'm demonstrating with g is 10 here, showing you that you could put g in as 10, and then it makes the math a whole lot easier here, right? We get an answer here for t of 10 seconds, and we probably didn't even have to pick up a calculator. Hopefully didn't have to pick up a calculator to get the square root of 100, right? So again, this is another reason you might use g as 10. So my answers in this problem might be slightly different than what you got if you use g as 9.8. Okay, so if we look at now in the x direction, now knowing the time is 10 seconds, obviously if it's moving at about 80 meters per second sideways for about 10 seconds, it would move horizontally a distance of 800 meters. Okay, and so if we wanted to, we could go even further, and I could challenge you further and have you calculate now what this angle theta would be. In other words, what angle will that package now hit the ground? Okay, think about that, and you may want to pause the video again one more time and see if you can challenge yourself to figure out what that angle theta in this diagram here would be. At what angle will this package hit the ground? Okay, in the x direction, since there's nothing to push or pull in the package, keep in mind we're ignoring air resistance, so the x velocity is going to be the same as it was at the beginning. The x velocity at the beginning of the problem was 80 meters per second, which means at the end of the problem it's still going to be 80 meters per second. In the y direction, the original y velocity was 0, so if we can get the final y velocity, then we'll know the final y velocity component and the final x velocity component, and we should be able to figure out the angle there for the velocity vector, and that's going to be along, tangent to the path. So we'll be able to get the angle at which this, off the horizontal, that this package lands on the ground. So following through with that plan, v final x equals v original x, which equals 80 meters per second, no acceleration in the x direction. Okay, and now we look for v final y, and if we can get that, we can certainly use our inverse tangent rule to figure out the angle. Turning to the y direction, v final y squared equals v original y squared minus 2g times y final minus y original. We plug in what we know. V final y, that's what we're looking for. V original y, the package was launched in the y direction at a 0 velocity. It had no up or down velocity at all at the beginning. So that's a 0. G, roughing it out, is 10 once again. Y final 0, y original was 500. Being careful with our signs here. We need to be careful with our signs. And we get v final y squared equals 10,000. Now, when we go to take the square root on our calculator, all right, we're going to get an answer that's positive. But is v final y here really positive? If somebody was asking me for the final y velocity, it would actually be a negative answer here, wouldn't it? Because when this package lands on the ground, it's going in a rightward and downward direction, which means the y component for the velocity is negative. Right? So I really want the negative square root of this answer, right? If I'm dealing with the velocity. Fortunately, I'm just interested in the magnitude, really, for solving out for the solving out for that angle theta. But again, technically speaking, I want the negative root here. So this is why you always have to remember when you take a square root or an even root, whether it's a fourth root or a sixth root or whatever you're looking at, any even root could have a positive or negative answer. Your calculator generally by default tells you the positive root. Here, the final velocity is actually a negative answer. Okay. Anyway, now that we know that, we know v final y is negative, and we can solve out for v final y using this other equation if we wanted. Right? We don't have to necessarily use this one that I started with on the left. You might have said, well, gee, wait, v final y is going to be equal to v original y, which I know is 0, minus g times t. So probably even much easier would be to solve for v final y like I did on the right here. And you'll notice you get the same answer. So again, this stuff's very forgiving. As long as you're using correct equations and following correct rules, you're going to get answers that are correct. Okay? The way on the left, I had to pay attention because it didn't tell me on my calculator probably that I needed the negative root, but I did. Over here on the right, with this method, I got it only gave me one answer, and it had the negative sign in there. But either way, now wrapping this up, if I know v final x is 80 and v final y is negative 100, that means that this vector that's pointing downward and to the right, like that angle theta that's indicated there would be my working angle, right? If you imagine putting your pencil, well, we could actually do it here. I'll take my pencil and we put our pencil on the vector, right? And we take the quickest route to the x-axis. That's it, right? In case you can't see it in yellow, there's the red version of it. Okay, put your pencil on the vector and take the quickest route to the x-axis. Again, not this angle. That's not the working angle. The working angle is the smallest angle between the vector and the x-axis. And so that theta, how do we get that? We get that by doing what? We take the inverse tangent of the y part over the x part. In other words, the magnitude of the y component of the vector is 100, the magnitude of the x component is 80, and so 100 over 80, we take the inverse tangent of that, and we get our working angle. This working angle is the angle at which it comes in at. We could also figure out the true speed that the projectile was moving at. How fast is that package going to hit the ground? Well, square root of the components, square root of the sum of the components squared, so 80 squared plus 100 squared, and then we take the square root of that sum and we get 128 meters per second. So that package is going to be moving very quickly, very quickly. So we may want to make use of air resistance, right? If this was a real mission, we may want to do these calculations. We realize, wow, that's going to be moving so fast that whatever's inside the package could get destroyed. So we may actually want to, and in many times they often do, put some parachutes, of course, onto the package to slow it down. And of course, then that's no longer projectile motion, so that's a little bit different. And we'll learn more about that as we continue along in the course. So we'll stop here for today.